In this video, we're going to be looking at the second part of this example. And so in this part, we want to express that vector A in both cylindrical and spherical coordinates. So before we go to our next page, let's just note our vector A is defined here. Note that we have an X component, a Y component, but we do not have a Z component. So again, you can come back to this part of the video later or look in the notes on Canvas if you want to sort of follow along with the example. Okay, so let's bring that second part down here. So we want to express A in cylindrical and spherical coordinates. So of course what we're going to be doing then is two vector-to-vector transforms. So this is going to be a little bit messier in terms of having to write a lot than our point-to-point transforms, but not too bad. We're ultimately just going to be using the equations that we had we didn't even derive, but that we wrote in previous videos. So first let's look at finding our cylindrical coordinates, or our cylindrical vector, and we want our rho, phi, and z components. So our equation that we had from a previous video said that we're going to have this 3 by 3 matrix that we're going to multiply by. We have cosine of phi, sine of phi, and 0 in our first row. Our second row is negative sine of phi, cosine of phi, and 0, and then our third row is 0, 0, 1. And we're multiplying that by a sub x, a sub y, and a sub z. But of course now we have actual values for that. So our x component is y for this vector A. Our y component is the quantity x plus z, and we have 0 z component. So we get something that looks like this. So now we just do vector multiplication. So for instance, when we're finding our row component, we're going to multiply our first row by this column like that. So if we do that, we end up with a row is equal to y times cosine of phi plus the quantity of x plus z times sine of phi plus 0. Similar thing for our a phi, we multiply the second row by this matrix over here. And what we get is that our a phi is equal to negative y sine of phi plus the quantity of x plus z times cosine of phi. And then finally, for our a sub z, we see that that's just going to be 0 still. As expected, because z is the same in Cartesian and cylindrical. Now, of course, if we're finding our row components, we can sort of get rid of our cosine phi or our y term depending on the information that we have. So let's say we want everything in terms of our cylindrical components. So we don't want to have, for instance, this y, this x, and this z. So we want to get rid of that, so we just have our row component in terms of rho, phi, and z. Sorry, so we're going to keep z, we just want to get rid of x and y. So I misspoke a little bit there. So in order to do that, we're going to use our equations that x is equal to rho cosine phi, and y is equal to rho sine of phi. And again, what that's allowing us to do is get rid of these y's and x's in our equation. So if we substitute that, we get that our vector in cylindrical coordinates, a sub y, is equal to, so we're going to have some quantity, so we have rho sine phi, so that's our y, times cosine phi, plus we have rho cosine phi, which is our x, plus z, all of that times sine of phi, and then I'm going to close my brackets, and that is our row component, so we put that times our unit vector in the row direction. And then we're going to have a second term, we're going to have plus negative rho sine squared of phi, so that's y times sine of phi, plus, again we have rho cosine phi, plus z times cosine phi this time, and all of that is that's our phi component, so that's multiplied by our unit vector in our phi direction. And then we have 0 in our z direction, so this would be our a in cylindrical coordinates. Okay, so a little messy, but not too bad. So for the next part, now we want to look at changing this vector A to spherical coordinates. All right, so let's do that. So the same basic approach, but of course now we're going to have a little bit messier 3 by 3 matrix that we're multiplying by. So we want AR, A theta, and A phi. And the 3 by 3 matrix that we multiply now, for our first row, we have sine theta, cosine phi, sine theta, sine phi, cosine theta. So that's all our first row. For our second row, we have cosine theta, cosine phi, cosine theta, sine phi, minus sine theta, minus sine phi, cosine phi, and 0. So again, that 3 by 3 matrix is just the equation we had from a previous video. And now I'm going to put my components in Cartesian. So in the previous equation from a previous video, we had a sub x, a sub y, a sub z. But now we know a sub x is y. We know a sub y is the quantity of x plus z, and a sub z is 0. And again, we could have transformed directly from cylindrical to spherical, but maybe we made an error in our previous work, so we can go ahead and transform directly from Cartesian. All right, so if we multiply all this out, again, same basic procedure for our R component. We multiply our first row by this matrix here, and we get that a sub r is equal to y sine of theta cosine phi plus the quantity of x plus z times sine theta sine phi. Similar thing for our theta, except now we're looking at the second row in that 3 by 3 matrix multiplied by the following matrix. We get y cosine theta cosine phi plus the quantity of x plus z cosine theta sine phi. And then finally for our phi component, we get negative y sine of phi plus the quantity of x plus z times cosine of phi. Okay, so a little bit messier. Again, we run into the same issue where if we're talking about our spherical coordinates, we'd like to not have this y, x, and z floating around. We'd like it to just be r, theta, and phi. So we want to get rid of all of these guys here. And so of course we can do that by substituting our expressions we had in a previous video. We know x is equal to r sine theta cosine phi. We know that y is equal to r sine theta sine phi. And we know that z is equal to r cosine theta. So if we take these expressions and we substitute them in the areas highlighted above, we get something that is truly a mess. So we get our vector A in spherical coordinates is equal to, so for our first component, I'm just going to go ahead, you can sort of double check by yourself, but I'm going to make these substitutions and go ahead and simplify some terms a little bit. We have r sine squared of theta cosine theta, sorry, I was right the first time, cosine phi sine phi plus the quantity of r sine theta cosine phi plus r cosine theta times sine theta sine phi, and all of that is just for our r component. So we multiply that by our unit vector in the r direction. So now on to our next component, our theta component. We have r sine theta cosine theta sine phi cosine phi plus r sine theta cosine phi plus r cosine phi, or sorry, r cosine theta. So that again is that recurring x plus y term just converted, and all of that times cosine theta sine phi. And so that mess is our theta component, so we multiply that by our unit vector in our theta direction. And then finally, we're ready to get to our third component, our phi component, which is going to be negative r sine theta sine squared of phi plus r sine theta cosine phi plus r cosine theta times cosine of phi, and all of that multiplied by our unit vector in our phi direction. So that big mess there is A in our spherical coordinates. In the next video, we'll come back and we'll finish with part 3 of this example.